Afternoon session. Our next speaker is Antti Kupiainen on linear diffusion in a random environment.
Okay. I want to thank the organizers for the invitation. Also, I want to apologize for some of them since they have heard already this talk.
Doesn't mean we understood it.
Okay, so if I get the same questions again, then let's see. Okay, so this is joint work, mostly in progress, hopefully finishing in the near future with Jean Bricmont. So the title is Nonlinear Diffusion in a Random Environment. So if you think about diffusion, then in this conference we have heard already some aspects of the classical problem also. So diffusion under suitable randomness is stable, as well as under suitable nonlinearity. So what I want to talk about is the combination of these two effects. And now you might wonder why should I worry about that? The motivation comes really actually not from starting from a diffusive model, but rather to try to derive diffusion from conservative dynamics. So from dynamics which is not diffusive, at least on the outset. So the sort of problems we want to discuss are problems where you basically only sort of energy is diffusing, you don't have energy is transported, not particles or other conserved quantities. So that I'm thinking about systems which are on a lattice. So at each lattice site I have some dynamics. Let's imagine that you have sort of Hamiltonian dynamics at each lattice site, and then you couple these Hamiltonian systems to each other. So your full dynamics is the dynamics of the subsystems and then some interaction. And now if you think about the interaction turning off the interaction, then the energy, the Hamiltonian of each subsystem, is a conserved quantity. So you have infinitely many, in the case of infinite lattice, conserved quantities. But once you turn on the interactions, then typically what happens is that only the total energy is conserved, and the local energies get slow dynamics, which you would like to show to be diffusive. So that's the sort of basic issue what I would like to address. Now you can look at it, and this has been looked during the years in many models, and sort of the simplest. I'm only talking about classical diffusion, not quantum diffusion. But as you can imagine, many of these things have their counterparts there. But think about classical thing. Then there has been a lot of study of coupled flows. So thinking about coupled oscillator models, if you wish. So an example of that would be just taking a nonlinear wave equation, but take it on the lattice. So at each lattice site, you have the field, and that satisfies a second order equation like that. So that's just a bunch of harmonic oscillators with a little bit of unharmonicity if the coupling constant is small, and then they are coupled together by the Laplacian. Laplacian is just a lattice Laplacian. So there's lots of numerics about these things, and lots of interesting phenomena which I'm not going to talk about at all. What one typically is interested in here is that once you turn on the lambda, the nonlinearity, then the system transforms from a completely ballistic or superconducting state to a diffusing state, and you would like to study the diffused state.
R here is just a constant. There's no randomness here, right?
No randomness whatsoever. I mean, for you guys, I mean, the randomness is sort of hiding in the fact that this is nonlinear, so that's going to act like a random. Think about that as a Schrödinger equation. Then this is u times u squared, and the u squared should, in some sense, act like a random.
So the u cubic will already produce, I should already see diffusion?
That produces diffusion numerically as well as R, as long as R is non-zero. When R is zero, then it depends on dimension.
So if I take an initial wave packet.
If you take energy, say, put it localized around origin, then that diffuses away in infinite volume. Okay. Now, so I said that's been studied for a week, small lambda, and you can take the kinetic limit where you take, and this is familiar for people in Schrödinger, random Schrödinger also. So you take the lambda to zero and at the same time rescale your space and time. Then, if you do it properly, you get in the end a kinetic equation.
Antti, I'm still confused about the first statement here. So this is if I do this in the continuum, I'm going to get ballistic behavior.
No, I'm on the lattice.
But the
it's important.
lattice is important then.
It's important to be on the lattice here. Yeah.
So if I'm in the
Continuum has lots of interesting problems, but they mostly take place in momentum space, not in real space like here.
So if I take this equation and I go into continuum space,
Yeah.
I will get.
The next talk, as far as I understand, will discuss this in continuum, and then the interesting phenomena are in momentum or wave number space.
That's right.
Okay. So transport is in wave number space. Here, the
if I
transport
look
is
at
in
this problem in the continuum, then if I look at wave propagation in the continuum, I would get ballistic behavior.
taking the infinite volume nonlinear wave equation.
Yeah.
Presumably, yeah.
So the effect you're talking about here is lattice dependent.
This is a purely infrared effect. So I don't know what happens if you go to the continuum limit of that equation.
Okay, so
I don't think.
All right. No, I would claim that that's a
In the continuum, it's rather. What happens is you get transport of energy and particle number in wave number space.
Okay.
But I'm not going to talk about these things at all. So
Okay.
This was supposedly, some of you had heard talk about these things, so I wanted to connect to it. What I wanted to stress here is that this is weakly nonlinear system, so you can do some calculations, arithmetic calculations, but if you try to prove something there, it will be very difficult, because this is a system with lots and lots of very weak chaotic properties. Except once you start coarse graining, you believe it to have nevertheless this diffusive behavior. So if you do this kinetic limit, then you actually you get something, a kinetic equation, you get diffusion and transport loss. However, it's very difficult to prove even the existence of a kinetic limit, not to mention the corrections to that. So what we want to discuss is rather completely opposite situation. So here we had weakly nonlinear, strongly coupled systems. So I want to rather take weakly coupled, so this thing will be small, and strongly nonlinear systems. And actually, the idea being that you have very strong local chaotic behavior, and then you couple these things together. So here is a picture of an example of such a system. So you take, you play billiard on the white region, put a billiard ball on each table here, and your parameter, the coupling, is this aperture here. So when it's when it's zero, then the billiards don't know of each other. Each of them just has its own energy conserved, and that's it. Infinitely many conserved quantities, if this is an infinite lattice. And once you start opening it, they might at some point start colliding every now and then, exchange energy, and as a consequence, there is not any more conservation of the local energies. The only conserved quantities is actually the total energy. So then start with an initial condition where you have sort of uniform distribution, except you put some bump in the middle and ask what happens to such a state. Okay, so that would be an example of a model, a Hamiltonian model, which you expect to have first of all only transport of energy, and that transport should be diffused. So, so in that model and in the whole class of things which we are thinking about, the total energy is sum of local energies. Each of them are conserved if you have no coupling, and once you turn on the coupling, they are not anymore conserved. The time derivative of the local energy will be divergence of a current, and the microscopic current, energy current, heat current, if you wish. So there's a flux of energy at each site, and what you would like to show is that this equation, in the end of the day, even if it doesn't look like that, is like a heat equation, and this current here is actually tied to the H by something called the Fourier law. More precisely, take an infinite system and take an initial condition so that your energies tend to constant at infinity. Then you would like to show, so they tend to constant at infinity, so there's some bump in the middle. You would like to show that as time proceeds, they deviate from this constant ever so, in a diffusing manner, namely by this heat equation type behavior. Another way to say this is to take the initial condition instead of taking bump at fixed scale, take the initial condition at scale, very long scale, so put a little parameter here, fix a function, and take the initial condition on a 1 over epsilon distance scale. Then do the dynamics, but rescale space and time, time by epsilon squared, space by epsilon. And then you would like to show that these guys weakly converge to some function in the continuum, and that function would satisfy a nonlinear diffusion equation, and the current, what we had there, would converge to something which is tied to this gradient of the tau variable, the temperature, by this function of tau times gradient of tau. So that's the analog of the of the statement of taking hydrodynamic limit in this system. So these statements should both hold for almost all initial conditions, actually, in the systems what we are discussing. So for almost all, with respect to the Liouville measure of the Hamiltonian system. We are, of course, in infinite volume.
You could have, so you're talking about that there is some spread of the energy,
yes,
right? But you could also have, I don't know. So, but could you have a trace of some, maybe not in this system, you might imagine having a trace of some localized stuff left behind.
Not in this system. That will be measure zero if there will. Of course, in finite volume you have periodic orbits and things like that. But I mean, if I'm thinking about infinite system, then this is literally going to happen for all infinite time scale. You can do the same thing in a finite system by putting noise on the boundary and looking for a stationary state. So take a system which is sort of a big box on the lattice. Put epsilon here. Put some noise with energy, little t on the boundary. Rescale everything. Look at the stationary state of the noisy system, and again compute the same objects as before, and then you would have stationary version of the same question. So you would have instead of things going to zero, they would go to whatever is the energy profile consistent with the boundary conditions. Okay, so that will be the stationary state formulation of the same question. Okay, so what I will discuss is some toy models for this. I'm not going to do the billiards. That's certainly much too difficult at the moment, although certainly doesn't look as bad as the coupled oscillators. What I would want to do is I want to cook up a deterministic dynamical system which is sort of mimicking what I just told you about. And I will do it in, not in continuous time, but in discrete times. I will take maps instead of flows, and I'm thinking about having maps which are very chaotic locally, and then putting couplings to them in the same way as sort of mimicking what I was describing before. So that's in the context of coupled map lattices. So coupled map lattice just means that you have a variable at each lattice site, and when you don't couple it, this variable just all of them have the same dynamics. You could have also different, but let's take a translation invariant situation. All of them have the same dynamics, and then you put some parameter there, which like the aperture in my picture, which then couples the systems together, and you have in general a map just from the whole phase space to itself, which you want to do nevertheless sort of in a local manner. So let's say nearest neighbors. This map depends on what is the updated value of m at site x will be just depending on the nearest neighbors, or at least short range in the neighborhood of x. So the coupled map, what I would be considering is tailored to what we had before. So think about the billiards. What would the billiards be? At each billiard you have sort of it's a chaotic system, so it has zero Lyapunov exponents. There is the conserved quantity energy, of course, and there is the time direction. But since I'm thinking about the maps, I will have just basically one conserved quantity, and then the rest should be chaotic. The rest is the Lyapunov exponents are positive, and there is chaotic dynamics for the rest of the degrees of freedom. So my uncoupled dynamics, just the toy model of the single billiard would be energies are conserved, nothing happens to them, and then the other degrees of freedom, let me call them theta, obey some dynamics. So I will call this variable energy, and this variable is something else, and my model will be just to take this something else, something which I understand perfectly well. So take some your favorite chaotic system like doubling of the angle or Arnold map of the torus. So then the theta part of the dynamics is fast dynamics with completely hyperbolic behavior, and the other dynamics has no dynamics at all. And now I want to write a couple these things together with a constraint that I want the whole total energy to be conserved. So how do I do it? Well, in general, it would be something like that. So here is the uncoupled. So these are the new e's after one time step. They depend on the nearby e's. So let's take some function which depends on all the energies, but mostly on the energies near the site x, the nearest neighbors, for instance. The same thing for the chaotic degrees of freedom. Maybe you want to couple them too. And so in general, in the case of billiard, I should have something like that. Of course, all the details are what on earth are these and what are the variables. But they certainly should satisfy certain properties that they depend mostly on the nearby guys. That should be true in the billiard case also. They should be isotropic and under translations and rotations. Since my system, I take my system translation invariant. And the only other condition what I want to impose is that energy is conserved. Namely, that will be the case if these guys, no matter what the values here are, sum to 0 as I sum over the lattice. So this is this is guaranteed, of course, if I take it to be a divergence of something. Here everything is on the lattice, so this is a discrete gradient here. So then the total energy will be conserved. Okay. So in this situation, I want to prove, let me repeat again what sort of statements I would like to show. I'd like to show that the thing diffuses, namely, if at infinity I go to constant, the deviation from that should go in the diffusive manner. That's the same thing to say that once I rescale it, so look at it at long times and rescale space, that goes to some fixed behavior, just a Gaussian. That would be a pure diffusive behavior in the scaling limit. Now I would like to do the same thing for the hydrodynamic limit. That would be exactly as I said in the previous case. Now,
could you just flash back? So this is the statement you're going to prove, or
this is the statement I want. I'm mostly that's what we are.
That's what you prove.
Well, that's what the proof hopefully emerges at some point. No, this is something which we are sort of confident in proving. This actually will not be much different, but that I haven't really looked at that very much.
So, so this is just no randomness in the system except through the dynamics.
Exactly. Yeah. It's a completely deterministic system. Okay. You want to show it for almost every initial condition. Okay.
Do I think of my? Oh, you think? So you.
I give an initial condition for the energies, and I want to prove it for almost every initial condition of the chaotic variables.
Do I imagine my initial condition is a local perturbation of this only, or what?
Here, the initial condition is that the energy goes to constant at infinity.
And you don't care how it goes to that?
Oh yeah, I want it to be L1. Yeah.
Okay.
Now, let's look at it a little bit more close. So there are these two dynamics. The first, let me not put the energy dependence here. That makes a little bit more headache and doesn't change very much. So let's let it just be that they talk to just themselves. So I take these totally chaotic systems and couple them together. If my coupling, remember the coupling is supposed to be weak here. Since it's this aperture, I'm thinking about putting very small coupling. So this will be something small, and as long as it's some smooth function here, then I still have a hyperbolic system after the perturbation. I have the space-time system, so these are space-time mixing dynamics. That means that if you look at, say, the connected two-point function, it decays both in time and in space. Okay, exponentially in time and space. So the fast dynamics is very nice. That's because I chose it to be completely hyperbolic. So if you take some smooth observables of the thetas, then you have exponential decay in space and time. So these fast variables provide a space-time dependent random environment for the slow variables. Namely, if I pick the initial condition typical from the invariant measure of the thetas, then that's the same thing as having a random environment with space-time decay and correlation.
So this first statement is just follows from
This one.
Yeah.
This one, basically, once you have a small perturbation of that, you can write the invariant measure as a Gibbs measure of high temperature spin system, and it has all the mixing you want. This is sort of old story. Okay, so let's just take my word that that's the case. So,
Okay.
so we can think about the chaotic variables as random variables, actually.
Is this some rigorous statement?
Yes, that's a rigorous statement.
It's a rigorous statement.
Yes. Yeah, that was.
Got enough mixing in the system.
Yeah, these things were done in the mid-90s. There, Jean and me wrote many papers, and the whole thing was studied by Bunimovich and Sina in the 80s. So there's a long history about that. So think about the slow dynamics. That's what we had. I told you that this is like time derivative, discrete time derivative. So without the coupling, you just had energies conserved, and now it was divergence of some function. That function depends on these random guys, these chaotic guys, and it depends on the energies. So these functions for fixed values of energies are weakly correlated in space and time. So what you have for the slow dynamics is you have a random nonlinear drift. So to prove that this guy diffuses for almost every initial condition on the chaotic guys is the same thing as to prove a quenched diffusion for the energies in this random environment. Okay, so that's the kind of problem we want to deal with. So if you want to understand what that looks like, let's first look at the annealed dynamics and not the quenched. So let's take an average over the randomness. Then, of course, once you take average, you get some other function. I told you that I want to take everything isotropic in, so translation invariant and rotation invariant, in order not to have drift. I want to get diffusion without drift. Of course, you could also try to deal with drift, but let's not try to make life too complicated. So in that case, this is a vector. The only way, due to isotropy, it will be 0 for constant energies. So in general, this thing for small gradients will be proportional to the gradient of E. So the average will have some form like that in all these systems. So the average, the annealed dynamics will satisfy a discrete nonlinear diffusion equation. Of course, depending on the model what you are looking at, this thing can be rather bad. Need not be at all an elliptic diffusion. What we will do is, of course, start with a model where this thing is nice. Okay, so then if you look at the quenched, then this was a true drift. So let's call beta the fluctuating part, so the thing where you subtract the average. Then the slow dynamics in the end of the day is given by a nonlinear diffusion and a random drift, where the drift has 0 average. So this is the model what we're going to now discuss. And what we want to do is to use renormalization to prove that the randomness is irrelevant, and also that the nonlinearity is irrelevant. And the long-time effect of all of this is just to renormalize the diffusion. So if, in yesterday's talk we had exactly such a model where things were linear in E.
But, sorry, could you go back to the previous one? So, you mean in Offer's talk, or what?
Yeah.
Yeah. So, but in his case, second term.
I'm going to discuss his case now.
Okay.
On the next slide. So his case was linear, namely, if the dynamics is linear here, So this is, if this is a linear function of E, then that's what it looks like. The new energies are just linear combinations of the old ones. By assumption, these guys conserved energy, they sum to 1. Let me furthermore assume that they are non-negative. If that's the case, then what I have as the linear problem is just a random walk. The new energies are gotten from the old ones by these transition probabilities of random walk. And the random walk and the energy itself is proportional to the probability of finding the walker at point x at time t. So you should think about my energies as the PDFs of random walks, and the rule here, the rule of the dynamics is the transition probability of the random walk. This is just random walk in random environment in yesterday's language. These guys depend on the thetas. The thetas, I told you, were random. Chaotic, which meant in particular that once I view them for typical thetas, these guys are weakly correlated in space, but not only in space, also in time. So this is inherently simpler problem than what was discussed yesterday. This is a problem where I have environment which not only doesn't know about distant space, I mean it's sort of locally correlated in space, but also forgets about its past. So I have a random walk in a rather simple random environment. Actually, even in such a case, in general, if you have a general such environment, it's not completely trivial to prove diffusion. So that's what we did some time ago. Let me explain how to do this linear problem and then how to translate it into the nonlinear problem. So you want to prove again, let me remind for the 10th time what you want to do. Let me take this reference energy to 0. Okay, so energies just go to 0 at infinity. So we want to do that. So it's the same thing as I told you. Equivalent way of stating that is that you want to show that the scaling limit is Gaussian. Scaling limit meaning if you look at it long time and rescale with the obvious factors, and you get the Gaussian. And you want to show that this happens almost surely in this random variables p. So for any particular realization of your environment, this always happens. Well, the way you do it, of course, in the linear problem is very simple to state that the energies at time t are nothing but just multiple applications of the same linear map p. That's, of course, nothing else but the transition probability of the random walk in time t. So if you want to see what the energy at time t is, it's just the energies at time 0, and the transition probability to move from y to x between time 0 and time t. And
so your walks are moving in a space-time random environment, or not?
Yes, I mean the environment depends on time. Yes, space-time random environment. Yes.
You didn't quite say. What are the assumptions on?
I will come
Okay.
to that. I want first to explain you that.
Okay.
So now I translate my statement to this. I want to show that these transition probabilities upon rescaling become just the usual heat kernel of the Laplace operator. That's what I want to show. And the way we do it is to use renormalization group, which is a tautology here. You see, we want to study this scaling limit. So let me give it a name. Call RL, the renormalized transition probability, to be looking at walks at renormalized times, t, which correspond to L squared unit scale times, and you go from Lx to Ly and you multiply by the appropriate volume factor. Call that the renormalization group transformation. That's mapping transition probability of a random walk to transition probabilities of new walk. And since I define it like that, there's a sort of tautological relation. If you want to study the old walk for long times and long space, it's the same thing as to study the new walk for shorter times and shorter space. So you trade, I write everything as a function of the random transition probabilities. So there's this random matrix everything is depending on. And I solve for the large time problem of the original problem in large times. I can trade that to study what happens to these transition probability matrices under such a map. So that's complete tautology, just notation. But it's a useful way to restate the problem. So you want to say that you take this random matrix, you apply this nonlinear transformation to it, and you do it again and again and again, and in the end of the day you want to say that it converges to a fixed point which is not random. And you converge it to no matter where you start with. Okay, that's the philosophy that you want to apply.
Now, in a usual renormalization group, is there an issue of relevant and irrelevant variables?
It will come, yeah.
Okay.
Okay, so what happens here is you can, in all these cases, you don't want to do it at a single stroke, but you want to do it iteratively to see how the randomness flows as you slowly change the scale. So instead of doing it immediately, do it with a fixed L and once and then repeat it n times, then of course in the end of the day you are doing the same thing as doing it for large L. So if I now do it, and every time after I've computed a new piece, call it Pn, I write it as an expectation, which gets renormalized all the time, and the random part, so this has zero average. Then I do it again, I get something which I put things in the expectation and in the random part. Then what you want to show is that the random part almost surely disappears, and the non-random part goes to the fixed point. So answer to your question, in the kind of simple problem that we are discussing here, this noise is irrelevant in all dimensions.
So you're saying a fluctuation about your annealed case somehow, right?
No, the anneal case gets renormalized all the time. These guys get
Yeah,
renormalized.
the fluctuation about it.
Fluctuation about the nth scale and renormalized.
Smaller.
So the equation sort of, the drift contributes to the diffusion constant at every scale, but ever so less and less after the scales increase. I mean, you can do a linear calculation, assuming that your noise is small. You can just compute the linear map, and I will not do it to you here, but what happens is that things actually contract very strongly under this renormalization. So, so what happens is that the covariance goes down by a fixed factor of the rescaling factor, and then of course you have unlikely events where things don't go down, but their probability will be exponentially suppressed.
Antti, do I understand correctly, you have to start with small dissolvent?
Sure, yes. Although in this problem, the pure linear problem, you should be able to do it for arbitrary disorder. And if you take, in the case of completely independent, in a Markovian environment that was done recently by Dalkupiot and Liverani. So maybe some things could become non-perturbative also in the nonlinear problem, but that remains to be seen. Well, let me repeat the same story for maps. I do exactly the same thing. So instead of having the linear problem where there was a matrix times E, I have now a map, in general nonlinear map. I'm interested in this scaling, so let me call these renormalized energies. Now that it's not so simple anymore that things are just, everything is in the transition probabilities. What happens is that these guys now satisfy, of course, renormalized dynamics, if you wish. So these are the energies at long different time scales, which are on the time scale L to 2n. So their dynamics, of course, is given by once I go from one scale to the next. The effective dynamics of the renormalized energies is the old dynamics applied L squared times and doing the obvious scalings. So in the linear case, remember, this was just the transition probability of the random walk, the matrix multiplied by L squared times and some scalings. Here are the same scalings, here the same thing, except it's the composition of these maps. And the only difference is that there is also the energy coming in. Once you do the scalings, it comes like that. That's very nice because you get this L to minus D here. So what you would like to show is, again, you would like to study these renormalized energies as n goes to infinity. And they are given in terms, their iteration is given in terms of the renormalized maps. So suppose you succeed proving that the renormalized maps converge to a linear map, namely just the fixed point of the linear problem, then the renormalized energies will then do what they did in the linear case. So that's what we want to show. We want to show that under this renormalization, the maps under the previous here, these maps become just linear in the limit. Want to show again almost surely. So we want to prove that noise is irrelevant, and not only noise, also the nonlinearity is irrelevant. So it's exactly the same iteration, except that now it's composition of these nonlinear maps. So let me write you what are the assumptions. At the moment, the assumptions are sort of that I take that I have a linear path, which doesn't have to be given by Kappa-Laplacian. I just wrote something concrete there. What I need here is any random walk which has sort of exponentially decaying transition probabilities. So that's the linear path, and then the drift. And of the drift, I assume various things. I want it to be exponentially decorrelated in x and t. I want it to be local, again, like we talked before. Translation and rotation invariant or covariant in law. But more importantly, I don't want it to screw the diffusion. So I want that this guy the bracket here is average. So if I take the square and average it, the L2 norm squared, I want it to be bounded by epsilon times. That's a weak disorder. So epsilon should be small compared to the kappa. So what I'm proving is the stability of this thing under such a random perturbation. I also need to assume something about of the E dependency. In what sense it is really local, etc. The most convenient way to say it is that this function is actually an analytic function of E in a strip. Why do I do that? If you look at my transformation, then clearly this really brings, wherever you start from, this seems to bring you into the small e region. And in the small e region, you would like to expand it and get sort of the leading terms in E out of this nonlinear thing. And it's very convenient if you assume analyticity. I don't think it's necessary, but it makes your life easier. You can also replace this by a nonlinear elliptic diffusion if you wish, but it doesn't make things any different. So why does it converge? Well, there are two things here. There's the old thing which I told you about the linear problem, but then there's also the nonlinearity, which is irrelevant. It's irrelevant. It's not completely obvious from here because there's the dot over L here. So this brings, it's not exactly as great as L to minus D, but once you do the calculation, you will see that all the nonlinear terms, if you are in a perturbative region of the E, all the nonlinear terms will be irrelevant. Not only that, your analyticity strip expands upon iteration, so eventually you are in the non-perturbative region wherever you start from. Now, it's not so simple because the randomness, you have this random drift which can, there are unlikely events where you can create arbitrary large E's. Okay? So you need to know that your anneal dynamics brings arbitrary large E's down. And you want to of course iterate that after n iterations the renormalized anneal dynamics still does that. Well, you are saved by the fact that you assume it in the beginning. Now the noise covariance goes down, so it changes less and less your anneal dynamics. So it's more and more hard to be in the large E region. So in the end of the day, you're saved by the two factors. The analyticity region expands, so whatever large E, it's finally in the perturbative region, and if you get even out of that, you are still brought down by the anneal dynamics. To write at least some concrete looking bound, so let me write how you actually do it. You have to localize these maps. I told you that this has to be a local function of the energies. I want to localize it also in the noise. It's very convenient to deal with sort of independent random variables. So what I do is that each of these maps I write as a sum of localized things. So this means that this guy is localized depends only on the energies in the region B, in the spatial lattice, and depends only on only on noise, if you wish, on independent noise in space-time region A, and you can do it so that these guys are independent once the space-time regions are disjoint. So you write it in terms of sum of independent guys, with the price being that this can be arbitrary non-local, but of course immediately when the space-time region for the noise is large, this will have very small covariance, and when you are far away from X in the E dependence, then again you are very small. So what you have is that the probabilities after n iteration step, you have such estimates. So probability that you are much bigger than what you would like to be, namely exponentially small in n, and exponentially small in all the spatial and temporal dependencies. Probability that you are much bigger is much suppressed. Okay, so to finish, if I go, that way you can sort of do these toy models where you have nice separation of the chaotic and non-chaotic degrees of freedom. In the true Hamiltonian system, at least I don't know anywhere you would have such a neat separation, so which would immediately fit into this language, this sort of assumptions what I have here. In particular, in the billiard case, what should happen is that you have rare configurations of the energies which slow down mixing. Think about that you are in one dimension and one of the billiard board is just almost not moving at all in the middle. Then it takes very long time for the energy to pass through that ball. You have to wait a long time. So there are configurations of E where mixing slows down. So even the anneal system, I don't think will be uniformly elliptic in such a case. The anneal system there will be E configurations where the anneal system is singular elliptic. So you have to deal with that, and in the same way, your random drift, you can have slowing down of your correlations. So the random drift can create not totally traps. I mean, these random walks are never trapped because you forget your past. But you can have very long lifetimes of traps, so you have to struggle with such things. All such things can, in principle, be studied with a renormalization group. In the end of the day, we are doing sort of a rather simple system where we had we didn't have, we had this fast correlations in time, and with similar ideas, sort of frozen systems have been studied. So that's not out of question that could be understood. Okay, so to finish, in the class of coupled map lattices, there is a derivation of diffusion from deterministic system, but of course from a toy model, which is very far from a real Hamiltonian system. Thank you.
Actually, Antti, so usually in the physics literature, you would derive a Green-Kubo formula, at least for the annealed system. Does a Green-Kubo formula for the diffusion constant come out of your?
There should be, yes. So that we can formally compute it. Now you're asking whether we have actually proven it, but we haven't even proven what I said here. So in that sense, no, it should come. Yes, this would be the perfect case to prove it.
Can you return to the initial equations that you had and explain what is in the end relevant as the relevant?
What is the initial equation?
Yeah, well, the coupled maps.
Here?
For example, what is irrelevant and what's irrelevant?
What is irrelevant and what is you see, it's not on the level of this equation.
So
well, if you wish nonlinearities in energy, I mean, this is a random function.
Yes.
Okay, so this random function, its covariance will be irrelevant. All its statistics will. The only relevant variable is if you fix the randomness, then you have drift, which is a relevant variable. But I will not have an average drift in the end because I will assume isotropy. That would be the only relevant variable. Then the nonlinearity will be also irrelevant. So everything will be irrelevant in the end. You don't have to fix anything. So in the end of the day.
No, so you can replace it by a linear equation?
In the end of the day, it becomes linear. In the long distances.
It becomes linear.
Upon scaling.
So how do I have? So why don't I have ballistic motion?
No, this becomes the heat equation. Linear heat equation. Upon scale.
The nonlinear diffusion coefficients, right? So evolution often leads to the sharp fronts, right?
Right, but here actually
Can you comment? I mean, would that cause any problems on the front because if the length scale goes to 0?
No, but you see here, in such a case, it doesn't. I mean, as long as this is positive, as I will always have. This can be an arbitrary bad function otherwise, but as long as it's positive, I won't have such problems.
So if it is,
it doesn't mean that my original billiard system wouldn't have problems like that. But in the class of systems, what I'm considering, I will always have this as a nice function. You're thinking about something where this is become singular, I suppose.
Well, no, like it's, let's say t squared, tau squared.
But that's singular at tau equals 0. I don't want to. That would be exactly the kind of case which would be interesting to study for the true Hamiltonian system. But then things get already complicated on the deterministic level.
That be of interest to have it frozen in time, or would you expect so that the standard information?
Frozen in time, well, I mean, then you really want to make your life very difficult, of course, because even the linear problem is difficult. But I think it would not be the right thing to think about here. I think here, typically it will be very far, at least in this kind of systems what I'm thinking about. You should think about that you have, to good approximation, the annealed system is uniformly elliptic. To good approximation, the noise is exponentially decaying in time. So the frozen would be sort of very strange configuration. So very small volume of the phase space would lead to something like close to frozen. So you want to show that those don't. And of course, numerically, you see nothing like that. Numerically, everything is perfect. And yeah.
So the lattice, the dimension of the lattice you use plays no role here, right?
No, it's all dimensions.
So, in the assumptions, do you need a fast enough rate of exponential decay in time, or for
No.
any?
No, but of course, if you start making that bad, then it might backfire in my nonlinear analysis. So, I mean, that's just order unity here. But actually, I would imagine it being much. An exponential decay should not be important here. As long as you have fast enough polynomial decay, everything should be still okay.
But I think that in the work of Liberani and company that you mentioned,
they have very fast.
it has to be fast enough.
They have,
if you don't.
yeah,
put
but they have
smallness
the
assumption.
but that's a non-perturbative result.
That's right.
Yeah. They have the result where they don't have small noise, but that's just because they are
If you don't have small noise, you have to have fast enough correlation.
for the
That's a
proof. For the
trade-off.
proof.
Yes.
Yeah, for the proof. But you don't believe that to be really the reality, right?
I don't know. I know at least a few proofs that did
Yeah.
that. So.
Yeah. Okay. Yeah. But okay. Here, I don't.
Okay. If you don't have